There's just never been an electric motor like this. I mean, you could pick this motor up with your hands, and it can accelerate a 2-ton car to 60 miles an hour in 2 seconds.
Tesla built an electric motor light enough to lift with your hands.
It happened on a stage in Texas, in front of an audience that believed they already knew what Tesla was about to reveal. There were no dramatic teasers, no carefully orchestrated media leaks, and no clues hidden in the weeks leading up to the event. Everything about the presentation appeared routine until Elon Musk stepped onto the stage holding what looked like an ordinary piece of engineering hardware. To most people watching, it was simply another electric motor. But inside the automotive industry, that moment quickly took on a very different meaning. Before we uncover why this small piece of engineering has become one of the most talked about technologies in the electric vehicle industry, take a second to subscribe to the channel and help us reach our goal of 5,000 subscribers. Within days, reports suggested executives across several of the world's largest car manufacturers had begun reviewing the announcement in detail, while engineers and analysts started asking the same question. Had Tesla quietly crossed a technological threshold that everyone else had underestimated? Whether those early reactions were exaggerated or not, one thing became clear almost immediately. This was no longer just another product launch. It had become the beginning of a much larger conversation about where the future of transportation was really heading. For more than a decade, the world's biggest automotive companies have been engaged in one of the most expensive technological races in modern industrial history. The transition from internal combustion engines to electric vehicles was never simply about replacing petrol with batteries. It represented a complete redesign of how cars would be engineered, manufactured, powered, and eventually driven. Established manufacturers such as Ford, General Motors, Toyota, and Volkswagen entered this race with enormous advantages. Decades of engineering experience, global manufacturing networks, and supply chains that stretched across continents. Against companies of that size and history, Tesla appeared to many observers as an ambitious newcomer that had arrived early but would eventually be overtaken once the established giants committed their full resources to electric mobility. For a time, that prediction seemed increasingly reasonable. Electric vehicles from competing manufacturers became more refined with every generation. Battery technology advanced faster than many analysts had anticipated, charging networks expanded, and established brands began producing vehicles that challenged Tesla on quality, comfort, and practicality. Industry experts openly questioned whether Tesla's early lead was simply the result of arriving first, rather than possessing any lasting technological advantage. The consensus in many corners of the automotive world was that competition would gradually erase the gap until electric vehicles became a market where no single manufacturer held a meaningful edge. Then, Tesla introduced something that shifted the conversation almost overnight. It wasn't another futuristic vehicle, an updated battery chemistry, or a new software feature. Instead, the company's engineers revealed a component that most consumers rarely think about at all: the electric motor itself. Yet engineers who examined the design recognized that this wasn't an ordinary refinement. Many reportedly reached a similar conclusion. Tesla had not simply improved an existing technology. It appeared to have solved engineering problems that much of the industry had accepted as unavoidable. The real concern wasn't only how efficiently the motor performed, but how extraordinarily difficult it would be for competitors to reproduce the same design at industrial scale. Even if rival manufacturers fully understood the engineering behind it, replicating the manufacturing process itself could require years of development. By the time that happened, Tesla would almost certainly have moved on to its next generation of technology. But why reveal such an important breakthrough at this particular moment? To answer that question, it's necessary to look beyond the engineering laboratory and examine Tesla's broader position within the market. While the company remained the world's most recognizable electric vehicle manufacturer, not every recent product had lived up to expectations. The Cybertruck, introduced after years of anticipation, generated enormous public attention, but also faced production challenges, recalls, and questions about long-term demand. Reports suggested sales were lower than many investors had hoped, and critics increasingly argued that Tesla's technological leadership was beginning to fade as competitors released their own electric vehicles. Whether that perception accurately reflected reality or not, it created pressure for the company to remind both consumers and competitors that Tesla's greatest strength had never been unconventional styling or marketing. It had always been engineering. And deep inside Tesla's research and development facilities, far away from the headlines surrounding the Cybertruck, engineers had already been working on a breakthrough capable of changing the discussion entirely. To understand why this motor attracted so much attention, it's important to understand one of the oldest limitations in electric vehicle engineering. For decades, designers accepted that every electric motor involved a difficult compromise. A motor could deliver exceptional performance with astonishing acceleration, or it could maximize efficiency and provide long driving range. Achieving both simultaneously proved extraordinarily difficult. As motors became more powerful, they generated greater heat, experienced higher mechanical stress, and required increasingly complex cooling systems simply to remain reliable. Designing for efficiency reduced many of those problems, but often came at the expense of outright performance. Across the industry, this trade-off gradually became accepted as a law of physics rather than merely an engineering challenge waiting to be solved. Tesla's engineers approached the problem from a different direction. Rather than accepting the limitations of conventional motor design, they began searching for ways to fundamentally change the stresses acting inside the motor itself. After years of experimentation, that search led to one of the most unusual features ever incorporated into a production electric motor: a carbon fiber-wrapped rotor. Hidden inside every electric motor is a rotor spinning at extraordinary speed. And as rotational speed increases, immense centrifugal forces attempt to pull the entire structure apart from within. Every additional revolution dramatically increases those stresses, placing enormous strain on the metal components. Conventional designs eventually reach a point where vibration, deformation, or catastrophic failure becomes unavoidable. For that reason, manufacturers traditionally limited rotational speed, sacrificing potential performance in exchange for reliability. Tesla attempted to solve the problem by surrounding the rotor with carbon fiber, a material developed for industries such as aerospace, where exceptional strength must be combined with minimal weight. Acting almost like a reinforcing shell, the carbon fiber wrap helped contain the enormous forces generated during operation while adding very little additional mass. The result allowed the rotor to operate at rotational speeds exceeding 20,000 revolutions per minute, levels more commonly associated with specialized industrial machinery than with passenger vehicles. Yet the achievement was never simply about spinning faster. Higher rotational speed mattered because the motor remained remarkably stable, while doing so, reducing vibration, improving efficiency, and converting more electrical energy into useful motion rather than wasting it as heat. In engineering terms, that stability may ultimately prove to be the breakthrough that separates this design from almost everything that came before it. The achievement wasn't simply that Tesla built a motor capable of spinning at extraordinary speeds. Engineers have pursued higher rotational speeds for decades. The real breakthrough was something far more difficult to accomplish: maintaining remarkable stability while operating under forces that would normally tear a conventional rotor apart. By wrapping the rotor in carbon fiber, Tesla wasn't just making it stronger. The design dramatically reduced vibration, kept the rotor precisely balanced, and allowed the motor's magnetic fields to remain far more consistent during operation. That stability, meant a greater percentage of the electrical energy stored inside the battery could be converted into useful motion instead of disappearing as unwanted heat, vibration, or mechanical losses. To most drivers, that invisible improvement would never be seen, but to engineers, it represented one of the most significant advances in modern electric motor design. This is where the competitive advantage becomes difficult to ignore. Every electric motor wastes some of the energy flowing through it. Part of that energy becomes heat. Part is lost through vibration, and part simply disappears through unavoidable mechanical inefficiencies. For generations, manufacturers accepted those losses as the unavoidable cost of building powerful electric vehicles. Tesla's design challenged that assumption. By recovering more of the energy that would normally be wasted, the company achieved something every automaker has been chasing for years: more performance without demanding a larger battery. The result is deceptively simple to describe, but extraordinarily difficult to engineer. The same battery delivers greater driving range, stronger acceleration, improved efficiency, and lower operating temperatures all at once. More importantly, that improvement isn't limited to a single flagship model. Every future vehicle built around the same architecture benefits from the same engineering breakthrough, allowing those gains to multiply across Tesla's entire product line. The advantages extend far beyond acceleration figures. Drivers experience the immediate surge of torque that electric vehicles are famous for. Yet the motor remains efficient during long-distance travel, compact enough to fit into increasingly sophisticated vehicle platforms, and light enough to avoid adding unnecessary weight. Perhaps most importantly, it requires significantly less cooling than many competing designs. That may sound like a small engineering detail, but inside a modern electric vehicle, cooling systems consume valuable space, increase manufacturing costs, and add considerable weight through pumps, radiators, coolant circuits, sensors, and electronic control systems. Every kilogram devoted to cooling is a kilogram that cannot be used for additional battery capacity, passenger comfort, or cargo space. By reducing the amount of cooling hardware required, Tesla simplified one of the most complicated parts of electric vehicle design while simultaneously improving overall efficiency. The world received its clearest demonstration of those engineering choices with the arrival of the Tesla Model S Plaid. During its public demonstrations, the numbers alone seemed almost unbelievable. From a complete standstill, the car accelerated to 60 miles per hour in less than 2 seconds, a level of performance previously associated almost exclusively with specialized hypercars costing several $1 million. Video footage from those demonstrations captured something equally fascinating. Automotive journalists, many of whom had spent years testing the fastest performance cars ever built, could be seen reacting with genuine disbelief. Some instinctively stepped backwards as the car launched. Others laughed, not because the performance was amusing, but because the acceleration exceeded what their brains had expected to experience. Yet perhaps the most remarkable aspect wasn't simply how fast the Plaid accelerated. It remained a practical luxury sedan, complete with comfortable seating, generous storage space, and the ability to travel hundreds of miles on a single charge. It achieved hypercar performance without sacrificing the everyday practicality expected from a family vehicle. Naturally, rival manufacturers wanted to understand exactly how Tesla had achieved those results. Reports suggest that engineers from competing automotive companies purchased Model S Plaid vehicles, dismantled them inside research facilities, and carefully examined every component. What they reportedly discovered was not simply a better motor, but a manufacturing process that would be extraordinarily difficult to duplicate. Producing carbon fiber-wrapped rotors at industrial scale is an engineering challenge in its own right. The manufacturing tolerances are exceptionally small, and even minor imperfections during production can render an entire rotor unusable. A defect that escapes detection can waste thousands of dollars in materials and manufacturing time before anyone realizes something has gone wrong. Tesla appears to have solved those manufacturing challenges years before many competitors had even begun seriously exploring similar designs. While much of the industry remained focused on battery chemistry and charging technology, Tesla quietly mastered one of the most demanding production processes in modern electric motor manufacturing. For decades, the automotive industry largely accepted that drivers had to choose between efficiency and performance. Faster cars would inevitably consume more energy, while highly efficient cars would always sacrifice excitement behind the wheel. Tesla's engineers approached that assumption as a problem rather than a law of nature. By fundamentally redesigning the motor itself, they demonstrated that both objectives could be pursued simultaneously. Even more importantly, they appear to have developed a manufacturing process capable of producing those advanced motors at a scale suitable for mass production. At that point, the conversation stops being about a single technological breakthrough and becomes something considerably more significant. It becomes a question of whether Tesla has fundamentally changed the economics of building electric vehicles. Inside Tesla's factories, particularly at Fremont, engineers have spent years refining not only the products themselves, but also the systems used to manufacture them. That distinction matters enormously because designing an impressive prototype is relatively common within the automotive industry. Producing millions of identical vehicles at consistent quality while remaining profitable is where even the world's largest manufacturers frequently encounter enormous difficulties. The history of electric vehicles is filled with companies that unveiled spectacular concept cars, attracted enormous investment, dominated headlines for months, and then struggled once full-scale manufacturing began. Building one advanced electric vehicle is an engineering challenge. Building millions of them efficiently, affordably, and reliably is an entirely different discipline. Tesla experienced those lessons earlier than almost anyone else. During its rapid expansion, the company endured years of manufacturing problems that nearly overwhelmed the business. Production bottlenecks, malfunctioning automation systems, supply chain disruptions, and repeated assembly line delays forced Tesla's engineers to rethink almost every stage of vehicle manufacturing. Those difficult years were often viewed as signs of instability. Looking back, however, they may have become one of Tesla's greatest competitive advantages. Every production problem forced the company to improve its manufacturing processes, and those improvements accumulated year after year into knowledge that cannot easily be copied. Today, Tesla says its next generation of drive units has been engineered not only for higher performance and greater efficiency, but also for something manufacturers value above almost everything else: manufacturability. Although the term sounds technical and unremarkable, it may ultimately determine which companies dominate the electric vehicle industry over the next decade. A motor that performs brilliantly inside a laboratory has limited commercial value if it cannot be produced quickly, consistently, and at low cost. Tesla's goal is reportedly to manufacture the complete drive unit, including the motor, power electronics, and gearbox, for roughly $1,000. Some competing manufacturers are estimated to spend 3 to 5 times that amount to achieve similar levels of performance. The difference is not incremental, it is transformational. When those savings are multiplied across hundreds of thousands or even millions of vehicles every year, the financial advantage becomes enormous, creating the kind of manufacturing efficiency that can fund future research, lower vehicle prices, and reinforce Tesla's technological lead all at the same time. And perhaps That's the most important number of all, not because of what it costs to build a single motor, but because of what that cost difference means when multiplied across an entire global manufacturing operation. Imagine the numbers for a moment. If one manufacturer spends between $3,000 and $5,000 to produce a single electric drive unit, while Tesla manages to build a comparable system for roughly $1,000, the advantage doesn't remain confined to one vehicle. It multiplies across every production line, every factory, and every model rolling off the assembly line. When that difference is repeated hundreds of thousands of times each year, it becomes billions of dollars that can be reinvested into research, manufacturing, new factories, and future technologies. This is the kind of financial advantage that rarely makes headlines because it happens quietly inside accounting reports and production facilities. Yet it is often the force that determines which companies lead an industry and which ones spend years struggling simply to remain competitive. What makes Tesla's position even more intriguing is that the company appears unwilling to treat any part of its manufacturing process as finished. Instead of protecting a single breakthrough, its engineers continue searching for new ways to remove cost without reducing performance. One area receiving particular attention is the elimination of rare earth materials from future electric motors. These materials have long been essential components in many high-performance motors, but they also tie manufacturers to supply chains that are concentrated in only a handful of regions, particularly China. At the same time, Tesla has been redesigning sections of its power electronics to reduce its dependence on expensive silicon carbide components, another material that contributes significantly to the cost of modern electric vehicles. Individually, these changes may appear modest. Collectively, they represent an attempt to redesign the economics of electric vehicle manufacturing from the ground up. For years, rare earth materials have represented one of the industry's most significant strategic vulnerabilities. Manufacturers may design remarkable vehicles, but if the supply of critical materials becomes constrained or more expensive, production costs rise almost immediately. Reducing or eliminating that dependence would not simply lower manufacturing costs, it would also weaken one of the largest sources of uncertainty facing the global electric vehicle industry. If Tesla succeeds, it will have solved another problem that many competitors still regard as unavoidable, making the company less vulnerable to supply disruptions while increasing its flexibility to scale production whenever demand rises. Each engineering improvement strengthens every improvement that came before it, creating a cycle that becomes increasingly difficult for competitors to interrupt. Lower manufacturing costs allow Tesla to reduce vehicle prices without sacrificing profitability. More affordable vehicles attract additional buyers. Increased demand raises production volumes, and greater production volume generates even more manufacturing experience, allowing engineers to discover new efficiencies that reduce costs further still. The process repeats itself again and again, not through dramatic breakthroughs every year, but through thousands of small improvements that gradually reshape the economics of the entire business. From the outside, competitors appear to be chasing a moving target. Every time they narrow the gap, Tesla appears to have already taken another step forward. Meanwhile, much of the industry's competition continues to face the harsh realities of large-scale electric vehicle production. Ford introduced vehicles such as the Mustang Mach-E and the F-150 Lightning that received considerable praise for their engineering and driving performance. Yet the company's electric vehicle division has also reported substantial financial losses while scaling production. Lucid Motors demonstrated that it could build some of the world's most technically impressive luxury electric cars, but sustaining production required continued financial support from outside investors as development costs remained extremely high. Rivian captured enormous public attention and investment with its adventure-focused electric trucks and SUVs, only to discover that expanding production efficiently proved far more difficult than generating excitement before launch. Even established industrial giants such as General Motors and Volkswagen continue working through software delays, manufacturing challenges, and questions surrounding long-term profitability, despite possessing decades of manufacturing experience and financial resources that exceed those of many younger competitors. Viewed from inside the industry, catching up to Tesla looks far less glamorous than many headlines suggest. It is rarely about dramatic announcements or revolutionary prototypes. More often, it involves years of reducing financial losses, improving manufacturing efficiency, solving supply chain problems, and hoping to reach profitability before investors lose patience. Progress is measured not by spectacular victories, but by surviving another year while spending slightly less money than before. That is a very different picture from the one usually presented during vehicle launches and technology exhibitions. Among Tesla's global competitors, only China's BYD currently appears capable of challenging the company on a similar production scale, particularly in lower-cost markets, where affordability plays an increasingly important role. Yet, the two companies are pursuing noticeably different strategies. BYD has established a powerful reputation for delivering electric vehicles at highly competitive prices, making EV ownership accessible to a much larger audience. Tesla, meanwhile, continues pursuing a more ambitious objective: building electric vehicles that combine cutting-edge technology, premium performance, advanced software, and competitive manufacturing costs within the same product. Achieving only one of those goals is difficult. Achieving all of them simultaneously is what has made Tesla one of the industry's most closely watched manufacturers. At this point, the story begins to move beyond automobiles altogether. Most people still describe Tesla as a car company because cars are its most visible products, yet that description may no longer capture the full picture. Increasingly, Tesla resembles a technology company whose products happen to include automobiles. Its greatest competitive advantage comes not from any single vehicle or any single invention, but from connecting multiple industries into one continuously reinforcing ecosystem. Energy storage, battery manufacturing, artificial intelligence, software development, semiconductor design, charging infrastructure, robotics, and vehicle production all interact with one another, each strengthening the next. And remarkably, the electric motor introduced on that stage in Texas sits near the center of that entire system. The first layer of that system is data. Every Tesla traveling along roads around the world continuously generates information about its environment. Cameras observe road markings, traffic signs, weather conditions, intersections, pedestrians, construction zones, and countless unpredictable situations that no simulation could perfectly reproduce. The vehicles also record information about steering behavior, braking, acceleration, and countless other driving events. For autonomous driving systems, this information is invaluable because artificial intelligence improves by learning from real-world experience rather than theoretical models alone. With millions of vehicles operating across different countries and conditions, Tesla has accumulated one of the largest collections of real-world driving data ever assembled. Unlike many competitors that rely primarily on relatively small fleets of company-owned test vehicles, Tesla's customers effectively become participants in one of the largest distributed data collection programs in automotive history. Every journey contributes additional driving footage and sensor information that can help improve future software systems. The more vehicles Tesla sells, the larger that data resource becomes. More data improves artificial intelligence. Better artificial intelligence enhances